Alright. Okay. Um, what was I saying? Okay. I just want to do the tonight topic. It's not the comet. It's not a comet. It's Mercury. But during the past few years, I mentioned that amateur astronomers today are able to image Mercury sodium tail. This opened up a new sector of Mercury imaging. You just need a modest equipment like a small telescope on a tripod with a camera and with a sodium filter, which I would talk shortly. We're able to produce the image that you see on the screen. Now, it can be very striking because it does look like comets when imaging through the sodium filter. Now, I just want to back up a little bit. I just want to mention about the organization for Association of Lunar and Planetary Observers, which is also known as ALPO. It's an organization studies by amateur astronomy of the solar system. Within that group, they divide into many sessions. They have Mercury session, they have a solar session, they have Venus session, Mars, Jupiter, Saturn session, and also they have remote planet session, which consists of Uranus, Neptune, and Pluto. I'm not leaving Pluto out. And in addition to that, they have minor planet session, they have Aurora session, they have the eclipse session, they have Aurora, and just the one that just added momentarily, it's an extra planet section. Yeah, anything that do with the planetary system, we have a session there, even though extra planets deal with other stars. So anything planetary bodies in our solar system, we have session for ALPO. Now within that group, I am the Mercury coordinator for the last 23 years. What I do is, I just collect observations, analyzes, and report it to the journals. And in addition to that, I observe Mercury myself. Now, the next one, it would just end. That Saturday morning, I had a chance to image Mercury. It was taken in daylight, and the sky was pretty good, was nice and clear, and all was around 9, 10 o'clock at night during the day. And I was able to find Mercury in daylight with the help of the last quarter moon. Now, I set up the coordination and make sure it's in focus, and I swung over to Jupiter. Jupiter was bright enough to see in daylight through the telescope. It was almost right on the meridian, the highest point in the sky. And I set up the coordination, and also I set up the coordination for Mercury. Now, once I set that up, that helped me to find where Mercury should be. So I swung the scope over to where Mercury should be, and within a minute, I found it in a low power eyepiece. And the scene was almost excellent. There was a lot of turbulence here and there, but most of the time was excellent. Then I went beyond that to take a couple of images and hit the shot there. If you look carefully, you probably see some of the features on the disc and all, and I have yet to identify it. The one on the left, my image, and the one on the right, it was taken by the Messenger spacecraft, which is orbiting around Mercury between 2011 and 2015. And that's what Mercury should look like on the day I observed. So it looked almost identically. And you can see the white spot just below the center near the terminator and all. So Mercury was bright enough. It was just like minus 0.5. So it was bright enough to see in daylight. And it's about 22 degrees away from the sun. And the telescope was set up in the shade, and the roof blocked off the sunlight. So I was, pretty safe side. Observing Mercury on the safe distance from the sun and all. So, okay, so just one example of I do as a Mercury coordinator and as a Mercury observing myself. Okay. I can see the phone. Why did I show this? Because when I was growing up in Brooklyn as a kid, and my dad usually say, I remember he was saying that, oh, there's a Mercury comet down the block. There's a Mercury comet down the block. About 2 years before I got into astronomy. And he kept mentioning that. And I was like 7 years old. And he showed me one time, he showed me the car down the block. All right, it's a car. But I remember he did say that the Mercury Comet, that's a classic. That's a 1963 Mercury Comet convertible. And I'm very sure I'd like to hand on that car and drive around with it. It's a convertible too. And I don't know if any of the old timers remember as a kid that used to be a very popular car. This is a classic. So, so anyway, let's talk about the real stuff. All right.
Frank, when you're off the screen, we can't hear you.
Oh, okay. You hear me now?
Yes, perfectly.
Okay,
Whenever we
all
can
right.
see you, we can hear
Yeah.
you.
Okay. All right. What you see here is just a photograph of Comet Helen Bob. At that time, it was the brightest, -1 magnitude ray of the sunset. It was brilliant. It's still the brightest comet since that time. You know. And the next one is Comet Neowise 2020, just a few years ago. I'm pretty sure many of you remember this. I think that's one of the best comets till today, and it was visible early in the morning sky. Then it swung around the Earth, and it was visible in the evening sky right after sunset. So this was taken in the morning sky, and momentarily, about a week later, it was visible in the evening sky. You can see the tail shifting away, shifting in a different direction. So this is that's what a real comet looks like. You know. Okay. Then the next one, it's not a comet, right? Well, if you're not sure, is it the comet or is it the comet Mercury? So indeed, it's Mercury sodium telephoto bioamateur. This was taken 2 years ago. One of the Italian astronomer, Andre Alessandrina, he sent me this photograph. I don't have any photo information with me, but I just want to show you, what it look like, otherwise you get a little bit, taking a detail. I don't want to go into it, but it's like a simple telephoto lens on the tripod with the filter, and you're able to image like that. Now, let me spread a little bit scientifically about the sodium tail. Now, does Mercury have an atmosphere? Anybody? Yes? No? Maybe? Well, here's the fact. Mercury has the thinnest atmosphere of any planet in the solar system. The atmosphere is so thin that the scientists have another name for it, an exosphere. Okay. Now let's talk about a little bit about the history of how this came about. The idea of the sodium tail is not new, but the idea has been around for a long time. Back in the 1960s, some astronomers were suspicious whether or not if Mercury has an atmosphere. Both Venus and Mars contain carbon dioxide, CO2, in the atmosphere. Why not Mercury? So, in the 1970s, they did some spectroscopic work, and no carbon dioxide absorption was found on Mercury. Also, the Marlin 10 spacecraft, which flew by Mercury in 1974-75, did not confirm CO2, carbon dioxide. But it did detect other molecules like hydrogen, helium, and oxygen. Those are lighter elements. Therefore, Mercury might have an exosphere. Now, again, Mercury doesn't have an atmosphere like any other planet as we know. Okay? But it has an exosphere, and it consists of hydrogen, helium, oxygen, and other lighter elements. Mercury's gravity is strong enough to hold gas molecules onto the surface, but not strong enough to hold as an atmosphere. Now you have all these molecules They don't collide together. They bounce the surface and they shoot up in space. You know. Now, in the 1980s, the spectroscopic observations did confirm that Mercury has a heavier gas. Mercury now has the sodium, Na, molecules and dominating in the spectrum of 589.1 nanometers and 589.6 nanometers. It's the sodium double D line. It has a strong intense yellow color, which is sensitive to our eyes. So we can see the brightest sodium molecules more than any type of gas. Also, the filter is needed when it emits only in the sodium light. Okay, here's one example. Here's our own Steve Bellavia. 2 years ago, I able to image the Mercury sodium tail, and you can see clearly a close-up of Mercury, and you can able to see the tail. Not only that, you got the nearby crescent moon, which adds a nice view along with the Mercury sodium tail. Now you can see the lower box. That's what it looked like on the regional side image. But the close-up, you can able to see the tail and adjust the contrast, and you can see Mercury look like a comet. I've got several other pictures. Even there's some more images last year, April 24, 2022. And now probably got more, improvement or better technique to bring out the sodium tail. As you can see, it looks like a tail. It looks like a comet. Now, another person, John Van Drow from up Massachusetts, he took another shot of the sodium. He's another alpha member. And you can see on the right side, the open crescent Pleiades, and along with the Mercury and its sodium tail. So this is a nice combination of features here that you can see the Mercury tail, sodium tail, and the Pleiades open crescent in the same field. It's a fairly nice shot. And not only that, you can able to determine how long the tail is by looking at Pleiades. Pleiades is about maybe a half-mile diameter. So the tail, if you adjust the contrast and all, and you can able to see the tail is just a little more than half a degree length. You don't see this with the naked eye, only through the filter. You hit the close-up shot, and I think it's pretty neat. There's another observer, Sebastian Fosmer. He's a German amateur astronomer. He sent this picture to me. This was taken last year. It's kind of hard to believe. This is a really nice picture with the tail and the Pleiades nearby and all. But the funny thing about it, this is not actually a single shot. This is two shots together. When he did that, he imaged Mercury's sodium tail, and he did another image of the Pleiades, and he combined it together. But this is the actually distance from the Pleiades to the Mercury sodium tail. But with the sodium filter, you cannot take the Pleiades, the velocity, and it's bluish now. So he combined the two images together with two different filters. But the distance between the Pleiades and Mercury is correct. So, but that's pretty neat, though, two pictures together and with two different filters. Okay, here's another close-up shot. The same person, Sebastian Fosmer. He did one in color and one in black. It shows maybe a little bit more, but it got different sensitivity of the gas, of the sodium tail. The black and white images show the details on the gas very well. Maybe not much difference, but sometimes it brings out the different kind of contrast. Okay, here's another shot. It was taken last month. I mean in April. It was just Mercury just about setting, and he did a close-up shot, and it looks really fabulous. It's really incredible now. It's just like a new way of imaging Mercury. Now, okay, it hit a lot of images like Bellavia, but if you look closely, if the center of the tail, you can see like a little black straight line. That's actually Mercury's shadow projected against the sodium tail. That's pretty fascinating. So, okay, we have methods of spacecraft orbiting around Mercury at that time, and the spacecraft did able to detect sodium molecules. Um, this is the third flyby before they start to orbit. They did a flyby a few times. And they were able to image the Mercury and sodium tail, and you can see the intensity of the tail. But on the second flyby, you can see the tail is much more suspicious. You can see that the tail has a shadow projecting on the screen, you know. Um, so yeah, so they able to confirm that the spacecraft able to detect the sodium tail. Yeah, even from space, even from yeah.
Maybe you'll touch on this later, but do we know where the sun is in comparison to this image?
The sun is shining from the left side. The sun is shining from the left side.
Some from the left side.
Yes.
So could we infer then that you've got the heat of the sun on here, which is actually cooling the surface?
Well, no, they stretch it away. It's like a solar wind.
Okay.
The solar wind. It's like a comet. It pushes all the solar molecules by the solar wind, intense heat from the sun, and it just blew it away into space.
Okay.
Okay, so that's caused by solar heating, the solar radiation from the sun. It just pushes all the sodium molecules away from Mercury and will form like a tail. The same way as the comet. So you can see why is more intensity on the right, because Mercury has the elliptical orbit. Right? One point of the orbit is the closer to the sun, and another point of the orbit is furthest away from the sun. When it's closer to the sun, it picks up more solar radiation, and it causes the solar tail to form more visible, and you can see more intense heat from the sun all the way from the Mercury surface. When it's a little further away, it's not as intense, and the sodium tail is much shorter. Here's the close-up shot, and the blue circle is representing the Mercury disk. As you can see, the intensity of the tail. And what you can see on the right side, you can see like a little shadow projected on the sodium molecule pointing away from the sun. So, okay, here's another shot, but I don't think it's going to work. This is the short animation. So what you can see here, the blue circle on the upper left side, as Mercury going around the sun, you can see the intensity changes into very intense sodium tail, or when it's not too intense and the tail is shorter. But I don't think it's going to work. Try again. No. Okay. Now you can see Mercury orbit on the upper left side. You can see the elliptical orbit. When it's the closest, it shows the much intense tail. When it's the furthest away, it's not too intense and the tail is a lot shorter. But you were able to see it on the day better when you see it. So it just didn't work. I clicked the screen.
Touch the screen.
Oh no,
No,
no, it doesn't work. No, it worked last time. I don't know. Okay. Um, let's change. Let's do the sequence. Oh, you know why? Because they gotta be one of. There you go. All right. All right, now what you see here, this is the. You can able to see the double line here. This is on the wavelength of nanometers, and you can see it that it's on 589 and 589.1 and 589.6. Okay, these are the double sodium absorption line on the sodium light. This is where the filter emits just at that portion of the wavelength. Yeah.
The filter is between the 1.1 and 0.6, or it's just on 0.6?
No, the filters cover both absorption. Yes, yes, so they're together. Yes, yeah. All right. This is just a general review of the Mercury to show what Mercury made of. It's made of iron core, the mantle crust, and around there you see the cometary tail, and you can see that it's spread around the globe. So if you look on the bottom of the screen, on the right side of the screen, these are all the molecules that detect on Mercury. You have oxygen, you have sodium, hydrogen, oxygen, helium, potassium, and other type of gas. And the sodium is only considered 29% of the total molecule, but it's very dense and it's more visibly with the filter than any other elements, lighter elements. And this is just a general view that's surrounded by Mercury. You can see that the sun rays are from the left side of the screen, and you see that show all the elements shoot away from Mercury. And you can see the north cusp, the south cusp, and planetary ions. And you can see that has all the fields where all the molecules is located, and it just move away from the intensity of the solar radiation. All right. At one point during the transits, a lot of professional astronomers trying to determine if they're able to detect anything around Mercury limb. Now we know Mercury has a very exosphere, not an atmosphere. We know maybe they can be detected during the transit, but it's very hard to determine because I don't know if you're able to make it out, especially along the lowest limb. You can see it's not very as you can see the smooth light around there, but they cannot really confirm if they can be detected during the transit. It's not like Venus. Venus has the atmosphere, and you can able to make it out. So it's not really, it's not being confirmed, but they continue to, look for it in the next transit with a different kind of equipment to see if they detect any sodium molecules during the transit. And that way they could do an exoplanet when the planet move in front of their stars and see if they can detect sodium. So this could be the same way. Now, even the moon has some sodium too. They have an exosphere, and a lot of people don't realize that. But it's not as dense as Mercury, but Mercury is close to the sun, and so that's why you're able to detect it easily. But the moon, of course, is much further away from the sun, but it's more spread out because the solar heat is not as intense. And if you have I don't know if it can be detected with a sodium filter if you have one, but you need a special kind of telescope to be able to see any sodium molecule around the moon.
Frank, just remind me, Mercury is tidally locked to the sun, right? It's always the same face.
No, they have a very slow rotation.
solar.
Yeah, it's located in 58 days versus to 116 days. 1 day, one revolution
Okay.
on the sun. Yes. Yes. Um, so I don't really know anybody has taken any sodium picture of the moon, but it was done by at McDonald Observatory. Uh, as you can see how wide it is compared to the moon itself. Now, Jupiter Moon's Io has a sodium cloud too, but a small telescope popular with amateur astronomers was used to detect the volcanic event. Planetary Science Institute IO input and output facility, abbreviated IO and IO, is outfitted with the coronagraph, which reducing the intensity of the light from Jupiter and allow light coming in from the clouds of gas around Jupiter to be imaged through the special filters. This is supported by the Juno mission and Jeffrey Baumgartner of Boston University and he's a member of the Association of Lunar and Planetary Observers. Now, the first version of IO was designated by co-author Jeffrey Baumgartner of Boston University, who used it to detect the sodium cloud near Io from his backyard in the Boston suburbs. Now, the person, Morgan Taylor, said, I think demonstrated ability of this technique to work in such a high light pollution environment definitely helped to sell projects to the National Science Foundation. Okay, now I don't know how well you can see it. Okay, one on the right, it's a sulfur emission around Jupiter. But you see a black strip, and you see Jupiter itself in the center. Okay, those are the sulfur emission. Now, one on the left is the sodium cloud. Now, the sodium cloud, if you look carefully, you can see Io on the right side of the screen. You can see that's where the most intense sodium cloud was, because it's moving around with Io, but it can't be detected by the sodium filter by an amateur astronomer. The Io rotates about every 1.5 days, and so the strong magnetic field of Jupiter trapped the ring of sulfur ion, which you can see on the right, known as ioplasm, for showing the right planet. Okay, so with the sodium filter, under the proper techniques if you're able to do it, you're able to detect the sodium cloud. Okay, now even the Earth. Now look at the Earth. The Earth has 5 layers of the atmosphere. Of course, they have the troposphere, then they have the stratosphere, and you have the mesosphere, and you have the thermosphere, and you have the exosphere. Okay, this is some of the examples give you how to break down the Earth's atmosphere. Now the troposphere is basically the atmosphere that we live in. The stratosphere is a little higher up, where the high clouds located, and the commercial airline jets were able to fly. That's the stratosphere. But then you go up, then you have mesosphere, which most of the media are burn up in that portion of the atmosphere. Then you go further up, you have thermosphere. That's when most of the long satellites revolve around the Earth. Then you have the exosphere, which is it's the boundary line to space. That's where most, the space shuttle or something like that is located in the exosphere. Okay, here's another way of looking at it. Then you have the altitude, the kilometers, and you can see like the troposphere, and you can see the temperature. Of course, the higher you go, the colder it gets. And in the troposphere, you see commercial airlines, a lot of clouds located there. And Mount Everest, the polar peak, is almost within the stratosphere. Then you go, of course, you got further up, you got meteors burning up the mesosphere. You have the aurora hemisphere. It's located in that part of the atmosphere in the space shuttle. At that time, it was flown. And the exosphere, that's when most of the satellite, low orbit satellite orbit around the Earth is within that sphere. So the exosphere is it's approximately about 400 miles above the surface. That's when you enter in space. Okay, now this is the filter used for imaging the sodium tail. It's pretty pricey, but it's $155. It's by Thorn Labs. This is 1.5, 1.25 filter cells. They said the website. I don't know exactly the website, but if you go Google Thorn Labs, it will bring to their website. Then you break down into narrow filters, narrow band filters. Of course, Edmond optics, the cell sodium filter also, and so just Thorn Labs and Edmond optics that sell sodium filters for amateur astronomy. So I don't know how much it costs. So it's probably within $155. So, and the band pass is 581, 589.1.2 together, and the width is 10 nanometers. So it's not narrow, but it's not wide, but it's just enough to detect sodium light emit through the filter. Yeah. Okay, now Mercury is famous for not a comet, and that's it, folks.